Thank you very much. Thank you for the invitation. It would have been a pleasure to participate actually and not just online, but yeah, time constraints, etc. I could not come. That's too bad. So I wish you happy birthday remotely. And I'm also happy to see a few faces sort of far away in the audience. Some I recognize, so hi. Right, so I want to talk about measure rigidity of forms of SL2 to some power. It's a joint work with Lindenstrass. And there are a couple of mistakes one can make in giving talks. One is to never reach the actual theorem that one is proving. The other is that you never reach the idea that is the new idea in the current theorem. And I want to avoid both of these mistakes by starting precisely with the theorem that Elon and I are finishing writing up right now. So this is the statement. It's a specialized conference, so I really jump in to the full version of the theorem. And here it is. We take an irreducible arithmetic lattice in SL2R to the nth power. N should be at least 2. We take the quotient of this group, Lie group, by this irreducible lattice. We let A be the diagonal subgroup or diagonalizable subgroup of G of rank at least 2. What do I mean by that? So this A should contain a group isomorphic to C2 as a topological group. So it should have 2 independent directions. If it's connected or not, that's sort of not really important. What's important is that it contains a C2 as a topological group. Then it's at rank at least 2. We take an invariant and ergodic probability measure on the space with positive entropy for some element of the action. Ideally, we would like to get rid of that, but that has been the state of the technology for the last 20, 30 years, that in these kind of rigidity theorems, in this type of classification theorems for invariant measures, we can only do something if we have positive entropy for some element of the action. Okay, so those are the assumptions. And the conclusion is that one of two things is happening. Mu could be algebraic, by which I mean it's the uniform measure, the H measure on the closed orbit of some intermediate subgroup. Or the space is non-compact. The measure is invariant on the unipotent subgroup U, and mu is supported on a closed orbit of the one normalizer of U. That's the one normalizer is kind of a parabolic or even a Borel in this setting, a Borel subgroup of G. And this Borel subgroup has closed orbit, which only happens if the space is not compact. And your measure is sitting on this, which kind of reduces the problem to a solvable or even abelian situation. And the same simplicity of the space is not going to help you if your measure is supported on an orbit of a solvable subgroup. So that's the theorem. And yeah, I stated it in the real world. It would equally be true, and we prove it, of course, in the theorem, in the paper, in the general case, when you replace the reals by products of reals and p-adic fields. So that wouldn't make any difference to the theorem. Yes, and if you have questions, please interrupt me. Yeah, I know it's a little bit difficult, but go ahead. Let's try to make it as interactive as possible given the situation. Right. So this is the theorem. What's new in terms of old theorems is that the space has sort of rank n by taking the nth power of SL2R, but the diagonalizable subgroup is only assumed to have rank 2. And it could be completely arbitrary. It may be some diagonally embedded A, it might be a product of two Cardan subgroups of two factors. This all doesn't matter. And that's kind of the new statement in this theorem, because we had maybe over 10 years ago, we had general looking theorem, but where the A kind of needed to be the maximal diagonalizable subgroup. So this maximality is here really missing, and this is the full classification apart from the positive entropy assumption for invariant measures under subgroups that are invariant under subgroups of rank at least 2. Right. So as I was saying, the second mistake one can make is to never reach the idea. So I'll skip all the old ideas for the time being and jump in to the discussion of what is kind of the new idea in this result here. The proof is based on the product structure of the Levi measures and a new quantitative recurrence phenomenon, which we wish to explain. And before I go to this quantitative version, I go even back to more classical setting where I look at a measure preserving transformation on the space of dimension D. And Boschanitsan considered such a setting, just a measure preserving transformation on the space of dimension D in 1993, and he proved a quantitative recurrence result in this setting. And I want to start by sketching an easier version of this result of Boschanitsan, which kind of is what we picked up and applied in our setting. Boschanitsan works way harder than what I want to sketch. So he considers Hausdorff dimension of the measure and works with that. I just want to work with say upper box dimension, upper covering dimension of the space. And I'm not making everything super precise. Anyway, the first part is this kind of tower that is pretty elementary from the ergodic theory. You have your measure preserving transformation. You take any set A in X measurable, and you take an N in N, and you consider all the points in the point A, in the set A, so that the first return is after time N. Then the measure of that set is less or equal than 1 over N. And why is that? That's this kind of tower. You first look at the set, maybe you call this A equal 1. That's the set of all points that immediately return. Then you have A equals 2. That's the set, the subset of all points that return after 2 steps, and so on. A equals 3 and so on. And A greater equal N has sort of, maybe this is our A greater equal N for some version of N. And then you see that this, this set, which is here in the base, repeats here, and repeats at least N times before it comes back to the base. And that's precisely already the proof of that the measure of the set is less or equal than 1 over N. It's kind of a simple quantitative version of Poincare recurrence, which is an easy exercise in ergodic theory. Okay, and I want to now apply this to a space X that has dimension D in some naive sense. I don't want to go into Hausdorff dimension, etc. I'm just chopping up my space into R to the minus D sets of diameter R. So I'm covering the set X with balls of radius R over 2, and then by the definition of the dimension, I should have something like R to the minus D balls that actually cover the whole set. And I make it into a partition, why not? For each of these sets, we can apply the previous claim, this kind of tower. So for my set A here is one of these boxes. So one of these boxes is my set A, and then I look at the subset of this one box of all the points that don't return within time r to the minus d minus epsilon. So that's, I sort of used the dimension d in the formula, but I put some extra safety minus epsilon in. And then I apply the previous elementary result, and I see that the measure of the subset of this tiny box that doesn't have a return within r to the minus d minus epsilon has measure less than r to the d plus epsilon, obviously. Okay. I do this for every little box independently, and then take the union over all the boxes, which then means I have to take the union of r to the minus d sets, all that have measure r to the d plus epsilon as an upper bound in measure of r to the d plus epsilon. So if I take the union, I get a subset of measure r to the epsilon. I'm thinking of a small r. And then the next step would be that I set r equals 2 to the minus n, apply this for all n, and apply Borel-Cantelli. Right? So if I set r equals 2 to the minus n, and then I have r to the epsilon as my upper bound, I get an exponential estimate for the number of points that don't have a quick return. So if I now take the union over all the n's, I see that almost every point will be a good point for all but finite Lemma scales. So for almost all scales, but for almost every point, for almost all scales, I will have a quick return. And this is kind of a quick outline of a statement of that form. If x has covering dimension d, then mu almost every x satisfies when I look at the log of the first return of x in my dynamics to within r of the starting point x, and divide that by log of r, then the lim sup of that will be less or equal than the box dimension of the space. And as I said, Bolshanitsan's argument is more difficult because he works with the more refined version of Hausdorff dimension. But if you are just interested in a version of this statement, say using the box dimension, then the argument is really very straightforward, very simple. Okay. Now I want to sort of beef this up a bit. I want to make this stronger result in some ways. And most of all, I mean, my assumption here that I started with was that I had a single measure preserving transformation. And of course, in our context on homogeneous spaces, one often has a high dimensional group acting. So how about extending this to a group H instead of a single transformation, which is an R to the K. So H is isomorphic to an R to the K, again acts on X of dimension D, preserving the measure mu, and I made it a little prop because I'm not claiming that here all the assumptions are present that make this theorem true. I'm just saying this is the kind of result that with the right assumptions, definitely in homogeneous setting and so on, you will get a statement of the following form. So my acting group is now not a single transformation, but a group isomorphic to R to the K. The space is still dimension D, my measure is still preserved. And then mu almost every X satisfies something similar to the statement before. I'm looking at the first H return of X within R of little x. And this first H return is kind of a vector in R to the k, and of course I can look at the norm of that vector. So maybe I should, when the first return is a vector, maybe I take the norm of that vector, and then of this I take the logarithm. So I take the norm of the logarithm, a norm of the first return time, and then the logarithm of that, and divide by the log of the R again, and then the lim sup should be less or equal than the dimension divided by k. Because if my group is kind of higher dimensional, then the group, the bigger the group is, the more chances there are for the orbit to actually come back to the original point, right? So if this is my space, and here I have my R ball, and I'm walking out of the R ball with my H, and kind of there are many directions, that then these many directions sort of create lots of measure elsewhere, like in my tower, right? This tower argument was precisely saying, if you have the points that don't return quickly, they sort of create lots of measure elsewhere. And this lots of measure elsewhere is kind of helping you to put an estimate on the measure of the set of points that don't return. And if your group is high dimensional, then this creation of lots of measure elsewhere happens much more quickly. And this helps you to improve the statement here that when your so when your acting group is k-dimensional and the space is d-dimensional, then the speed of recurrence somehow will be d divided by k. K is helping you and d is hurting you. The bigger d is, the more balls you need to cover, and the harder it is to come back quickly. But the bigger your acting group is, the easier it should be for you to return quickly. So I'm not doing the proof of this, but it's kind of a continuous analog of what I explained in the lemma above. Okay, so how are we going to use this? We use this in a rather surprising fashion. And to explain how we use this, I want to simplify my setup from the theorem a bit, right? In the theorem, I said we have SL2R to the n, some arbitrary n, and some irreducible lattice. Right, I didn't say arithmetic. I said arithmetic, but I didn't. I only emphasize arithmetic here because it's actually important for the argument. It's built in anyway, but I wanted to emphasize it here because it's something that we will need to use in the argument later on. Anyway, yeah, I'm reminding you of this theorem. This is what we are aiming at. We are looking at this invariant measure for a capital A. The A is two-dimensional, that's all right. But maybe to simplify matters, I said n equals 3. And yeah. So if I said n equals 3, then the full diagonal subgroup is a three-dimensional group. But I want to just consider a diagonal subgroup of rank 2, sort of in general position diagonally embedded in the full diagonal subgroup. And then the roots of SL2 to the SL2R to the 3 restricted to this rank 2 subgroup could have the form of a hexagon. That's by chance the root structure of SL3, but of course the roots behave completely different because this root and that root, or this root and that root, they would commute because this would correspond maybe to the upper unipotent subgroup in the second copy, and this maybe corresponds to the lower unipotent subgroup in the third copy. So maybe these 1, 2, 3, these roots are the corresponding to the upper unipotent in the first factor, upper unipotent in the second factor, upper unipotent in the third vector, and then this corresponds to the lower unipotent one parameter subgroup in the first vector, lower in the second vector, and lower in the third vector. So this way you get 6 roots. But of course, every root that is labeled with every 2 roots that are labeled by different integers correspond to subgroups of different direct vectors, so they are commuting roots. So it's different. It's a different root structure than SL3, even though the picture kind of looks the same. Right. And I want to assume that my measure has positive entropy for some element of A. And yeah, maybe I explain it here. So this is the root. The roots, what are the roots? The roots are characters from the diagonal subgroup to the reals, which indicate the speed at which the corresponding common eigenspace is contracted or expanded. And if you identify kind of your acting group with the dual, you can also draw the elements of A in the same picture. So maybe here there's an element of A in A, and then this element A in A will, maybe I changed the direction a little bit. Maybe I take this direction. Then I see kind of a positive inner product with every root in this half space, which means that this particular A in A will expand the upper unipotent subgroup in the first vector, will expand the upper unipotent subgroup in the second vector, but will expand the lower unipotent subgroup in the third vector. That particular direction does that somehow, because I can see the inner product of all the roots with all these 3 roots with my A are positive. And the root is really telling me the speed of expansion in the corresponding subgroup. So yeah, it's kind of built in when you classify Lie algebras by the root structure. You're having the same discussion, so I don't want to go into great detail here about roots and so on. Right, and then now I need to quickly remind you of some of the setup that Elon and I and before Katek and Spazier have been using for these kind of questions. These 3 roots together describe precisely the full unstable horospherical subgroup. So if I collect these 3, I get the full unstable horospherical. And my assumption, my important assumption is maybe that H mu of A is positive. So the entropy of this element A is positive, which relates to how the measure and the full unstable horospherical subgroup sort of interact. So it actually tells you that there are lots of points that are typical for mu and are on the same orbit of the full unstable horospherical. So the complete opposite behavior would be if you have a measure supported on a periodic orbit of A, or a periodic orbit of the full three-dimensional A. If you have such a measure, then your space, let's draw our space again here. Here's my space. And then maybe I have maybe this is my first direction in capital A, and this is my second direction in capital A. And what could happen is that this kind of wraps up in both ways and creates just a torus in the space, right? That could happen. If this happens, then the measure would have zero entropy because it's just a translation on an abelian compact group. But the statement that I tried to explain here is precisely saying that if you have positive entropy, you're sort of not in this situation in a very strong way, because there's this three-dimensional transverse group corresponding to the full unstable horospherical group, and there will be lots of points on this three-dimensional full horospherical group. Okay, so that's in some sense what positive entropy means. That the measure is not completely ignoring the unstable manifolds. On unstable manifolds, you typically see many, many points that are typical for the measure. And because you're in the higher rank situation, one can actually obtain a stronger statement. And the statement then becomes that one can find one of the roots, maybe this root. One of the three roots will have the same statement for its subgroup. And that's kind of a higher rank phenomenon, which already is present in the work of Katok-Spartier from last century, and then in a stronger form appeared in a paper of Katok and mine, also about 20 years ago. So this implies also, but that already relies on higher rank arguments. This also implies there are lots of points on the same orbit of a one-dimensional root group. In general, one would have to talk about Coase-Lyapunov subgroups and so on. I simplified the situation so that I don't have to use all these words. Okay, so it could be another one, but my three roots, they really, if you permute your factors, the three roots really look the same. So I may as well assume that this guy here satisfies the stronger statement. And we also say that this root has positive entropy contribution somehow. That's another phrase that we have been using a lot. Okay. What we want to actually do is we want to use the recurrence phenomenon for this U, for this one parameter U, which has positive entropy contribution. And that's a little weird. Why? Because in this little proposition that I tried to advertise here, I had a group acting of a certain dimension, preserving the measure. Now I want to use this phenomenon for U, which is not preserving the measure. But in a sense, what's happening is that this positive entropy contribution claim that we established here by saying, okay, the three together have positive entropy contribution, but with higher rank, you can reduce it to one of them has positive entropy contribution. This claim, in some sense, amounts to saying that we have something like a group, well, not really, but we have something of positive dimension. Because the there are various ways in which you can define entropy, and there are many ways. That's precisely why entropy is such an interesting and important notion, because it has so many different definitions, and they all lead to the same quantity. And that's also happening here. We actually define something like a Lever's measure, which, okay, let me try to explain this a bit. So we again have our space, and now we have this one-dimensional U, which is not preserving the measure. It's sort of transverse to the A, and we have orbits of this point. Of various points, we have orbits. But of course, this point may be typical, but then lots of other points on this U orbit, they may be completely atypical for the measure, because there's no assumption for the measure and the subgroup U other than this positive entropy. So there's no invariance, nothing of that sort. But what we could do is we could take a long orbit and blow it up in the transverse direction to make it full dimensional. And then in this box, we have lots of little orbits like the one I drew. And we can restrict the measure to this box and look at the conditional measure of the measure restricted to the box along these fibers, which are pieces of U orbits. And of course, we would like to not just do this with one such box, but we would like to do this with longer and longer boxes. So maybe initially the box looks like this, and you only get a very tiny piece of the U orbit. And next time you sort of look at the longer piece, but you shrink it transversely so that it doesn't overlap with itself. So that, yeah, the conditioning sort of is most natural and easy. And then you sort of glue these conditional measures together, and in the end, you get a measure that's kind of on the infinite orbit and describes to you how the orbit and the measure interacts. Because maybe, so let me use a different color again for the measure. So maybe there's some density here and here, and maybe at the center point there was also some density. But in between there's sort of gaps in the measure. And then the Lever's measure, the conditional measure on the infinite orbit, would have precisely this structure, that maybe here there's some measure, then there's a gap, then here there's some measure, and then there's some gap. And it could be some Cantor-like fractal object, which you then get on this infinite orbit. Technically, what happens is that the conditional measures are always probability measures, but when you do this sort of this gluing together of these conditional measures, you will get something that is potentially an infinite measure on the orbit. And I'm trying to tell you sort of what this positive entropy here means, and positive entropy contribution. And actually what happens is you take this Lever's measure for this one parameter subgroup, and you apply it to a to the n one ball in U, a to the minus n. Remember, U is unstable, so this is a exponentially growing ball in the one-dimensional U. And it's kind of, yeah, checking how the large ball compares to the unit ball, say, in terms of this infinite measure. And you take this, divide by n, and then this converges to a positive number. And this positive number is the entropy contribution. And this growth rate, if you do this not for the one parameter unipotent subgroup, but for the full horospherical subgroup, this growth rate always gives you the entropy for your A. And this is kind of the entropy contribution of this one parameter subgroup. And And in that sense, you have some kind of positive dimension. You don't have invariance like in this little proposition. We don't preserve the measure. That's not true. But if you look at how much weight there is sort of elsewhere compared to where you are, this elsewhere has a growth rate. And that's precisely what this tower was doing. So when we looked at this tower, it wasn't so important that every little line here is the same measure. That was not important. It was important that the other lines together had lots of measure so that your line needed to have a certain estimate in terms of how small the set is. And this is what we can create with this leafwise measure also, once the leafwise measure have a kind of a growth rate. So this positive entropy assumption creates a growth rate of how much mass there is elsewhere compared to where you start. And with this, one can now prove a recurrence statement where, in a way, in this little proposition, the K is replaced by the entropy contribution. So this K here is not an integer anymore. It's the entropy contribution. The entropy contribution may not be 1. It may be 0.0001, but it's positive, so it's some fixed number. So it's okay. Okay. And so we can prove a common refinement of sorts of the quantitative recurrence theorem of Bosch-Schnitzen and of a recurrence theorem that Elon had proven is in his study of the quantum unique ergodicity conjecture. So he had precisely proven that if the leafwise measures are infinite, almost everywhere, then recurrence happens. And we are in sort of using the ideas of Bosch-Schnitzen in precisely this way to say that if you have leafwise measures are not just infinite, but they have a particular growth rate, then the recurrence can be made quantitative. Okay, so how do I go from there? So now I take a different A. It's a different A, it's an A0. And I take an A0 which commutes with the U that has positive entropy contribution. So this was my U from before. I made it orange. So this is my U from before. This one has positive entropy contribution. And now I assume, just for the moment, that the direction that's orthogonal to this U, which means that the A0 will commute with the U, this one actually has zero entropy. So that would be weird because it's not allowed in an algebraic version, an algebraic measure. If my gamma is irreducible, that just would not possibly be possible. But let's just assume for the moment that the A0 has zero entropy and the U has positive entropy contribution for the other A. I mean, I had here a different A, and this U has positive entropy contribution for this other A, but for this A0, it doesn't contribute because it commutes with the A0. So let's assume that. Then, as I said before, entropy has many different ways of manifesting itself. And one of these is that you can look at ball balls. So you can take your A0 and then, so let me just briefly define what this is. So you take your one ball in G and then conjugate it and intersect the conjugation from k equals minus n to n. That's kind of a dynamical ball, which you see a lot in the discussion of topological entropy. And let's just call this the Born ball in G. And then you can take this, let's call it BA0. I use this for A0, and ornament it with n somewhere. Maybe I ornament it with n up there to make it different from a ball. And entropy is equal to, that's kind of a version of the Shannon-McMillan-Breimann theorem, and Brin-Kattok have a statement like this, which is also called local entropy. So the entropy of A, which is 0 by assumption, can be defined in terms of these balls. So this is precisely the limit as n goes to infinity of the, you take the log of the measure, where you apply this to a typical point. You apply this Born ball, which is the Born ball in the group. You apply this to a typical point, and then you get kind of the Born ball in the space. Divide by n, and let's say we divide by 2n because we use the two-sided Born ball. Okay. So the entropies can be defined like this, but this is now 0. So that means that the Born balls for A0 have a sub-exponential decay. They may decay at some rate, but the rate of decay in the exponential range is just 0. Okay. That's kind of interesting, because if you know that your balls don't decay quickly, then it's very easy to cover the space. So this implies we can cover most of X by sub-exponential many Born balls, which are these things that appear here, B, A, 0, N applied to X. Okay. That's now weird. Let's go back to my little proposition. I said that the K was replaced to 0 by 0.0001 or something, because that was my positive entropy contribution from the subgroup U. But by assuming that A0, the other dynamical element, the other element of capital A, has entropy 0, if I work with Born balls, I could make this actually equal to 0. So I would get very, very, very quickly, I would get returns. The entropy contribution may be just a bit positive, and if it's a very small positive number, then the returns could still be very bad. But because my Born balls don't have exponential decay, if I make this weird assumption that the second element has entropy 0, in a way, my space becomes 0-dimensional, because it's very easy to cover the space with Born balls, because the Born balls have they basically have no decay in terms of the exponential scale, at least not. Okay, so I can cover the space with these balls, and we get the following kind of statement, which is a version of this little proposition for the setup that am working with. For mu almost every x, we obtain that for any d, let's think of it as a degree or something, and any large enough capital R, that's after applying sort of a Borel-Candelli argument, there is a return of x within the R ball of U to x, for which the displacement in the second and third factor is with an r to the minus d to the diagonal subgroup. Okay, where did this second and third factor sort of come up now? That's because of my simplifying assumption. I said that this is the group in the first factor, this is the group in the first factor, this is the group in the second, third, second, third. So this is the upper unipotent in the second, upper unipotent in the third. Okay. Now the Born ball will be exponentially shrinking in these directions, in the upper and lower unipotents. In the second and third factor, there's some exponential shrinkage happening. At the same time, so that's sort of a geometric statement that in the geometry of the Born ball, I have an exponential shrinking happening. But in the measure of the Born ball, I don't have exponential shrinking happening because my entropy of the second element A0 is 0. That's my assumption here. Okay. So if I convert this back from exponential to sort of a polynomial statement, then I get this kind of statement here, where I go up to capital R in the unipotent subgroup U, and in the second and third factor, I can return to the Born ball. The Born ball has been shrinking in the second factor and the third factor, away from the diagonal. In the diagonal direction, it may not shrink because the Born ball doesn't do that. If you look at the diagonal direction, this conjugation doesn't do anything to the diagonal direction. So this object here is kind of, so let me explain this here, A0n looks like, so in the first factor, I don't do anything because the A0 is commuting with the unipotents and also with the diagonal in the first factor. So in the first factor, it looks like the unit ball inside SL2R. Gross. Then I have some exponential shrinkage, e to the minus n SL2R, but multiplied with the one ball inside the diagonal subgroup of SL2R. So in the diagonal subgroup, I have no shrinking happening, and in the upper and lower unipotents, I have exponential shrinking happening. And the same thing in the third factor. So in the second factor, I have this kind of thing, and the third factor, I have the same kind of thing. That's sort of the geometry of the Born ball, that in the diagonal subgroup, it doesn't shrink. And in my particular case, because this A0 is orthogonal to the first root here and this opposite root, in the first factor, I also don't have any shrinkage happening, and I just get the one ball. Okay. So if I work with these Born balls and then ask what this return actually means, I get precisely this statement. So my capital R is kind of, R is e to the minus n, or something like that. So I switch from the n to the parameter R, and then I have for mu almost every x, we obtain that for any d, that comes from the zero entropy assumption of the A0, and for any large enough capital R, there is a return of x within the R ball of u to little x, for which the displacement in the second and third factor is within R to the minus d to the diagonal subgroup. And the d is kind of arbitrary. That's the crazy thing. And this statement corresponds to, when you now switch viewpoint, in some sense, to a lattice element that satisfies amazing differential properties. Okay, of course, sometimes you have lattice elements that satisfy maybe this or that type of estimate. That may happen. But what happens here is that for all large enough R, there is this lattice element happening to, which gives you some very strange, very effective return of the point to itself. And if you, for instance, what you could say is you get maybe you get two lattice points from two returns, maybe at slightly different scales. Then you can look at the commutator of these two lattice elements. And when you look at the commutator of these two lattice elements, you know what happens because you understand that this lattice is sort of related to size R in the first factor, and in the second and third factor, it's to within R to the minus D of the diagonal. When you now take two elements and you take the commutator, then let's call them, take gamma 1, gamma 2 like that. And let's take the commutator, gamma 1 and gamma 2. Then in the first factor, it will be R to the 4 big, will be of size less than R to the 4, because each one of them is created from this return when you went out capital R in the unipotent direction. And if you take the commutator of some two elements of norm R, then you get R to the 4. You might think maybe this commutator of unipotence is 0. No, but it's really, there's some displacement, some tiny mistake in the picture from the one ball, and hence only the thing you can say in the first factor is that you get R to the 4, because a tiny rotation can make commuting elements non-commute. But in the second factor, something crazy happens, and the same thing happens in the third factor. Because here you are within R to the minus D to the diagonal, and the diagonal is commutative. So you get that this is in norm, is R to the minus D close to the identity in the second and third factor. So that means when you look at this commutator, which is an algebraic object, and the first factor corresponds to the one Galois embedding, and the second and third factor correspond to two other Galois embeddings. If you look at this algebraic number, algebraic object, and you compare to the identity element, say you compare you look at the non-diagonal entries of the commutator. In the second and third Galois embedding, they are R to the minus D. And the first, they are R to the 4. But because of the zero entropy assumption, you can actually choose the capital D. So the capital T is for you to choose, because there are these fantastically quick returns. I said before that the zero entropy assumption makes kind of this lim soup. The numerator here becomes 0 because of the zero entropy assumption, which means that you have super fast returns, which means that you can choose this capital D however you like. And when you choose it large enough, 20 or something, then this kind of information implies that the commutator is trivial. So you get from an estimate, you get an equality. And this is also what Elon has been using in his quantum unique ergodicity paper, how he actually proved positive entropy. And yeah, so once you could improve it, the inequalities to an equation, you are in business to somehow say this doesn't make sense for it to happen again and again and again, because actually means something for this point x. The x was supposed to be a random point in the space for the measure, and now it has some very strong relationship to one and the same torus, because if the gamma 1, the gamma 2 commute, they define probably, they have the same centralizer because we are sitting inside SO2. And if we change the scale a tiny bit, then the same thing happens. And when you now let the scale go to infinity, meaning the little r go to 0 along some geometric series, then you will see that the x has a very strong relationship to, is sitting on a periodic torus orbit or something like that. And that can't possibly be true because x is supposed to be typical for this measure of positive entropy, and you actually get a contradiction to the setup. Because we are able to sort of convert the recurrence, the quick recurrence, to these amazing Diophantine properties. Yes, so that's what I said here. Now, this didn't prove much. This proved a contradiction to this assumption here. So you might say, so what? So this assumption leads to a contradiction. So that means that the A0 cannot have zero entropy, the A0 must have positive entropy. And then there is a tiny trick, and this tiny trick completely solves the issue. So instead of this, you should assume H mu A0 conditioned on some sigma algebra A is equal to 0. And if you choose your sigma algebra here correctly, then the positive entropy contribution will not change and the argument will not change. But the contradiction that then says, no, this is not happening, the entropy contribution, even conditioned on A, must be positive, actually proves unipotent invariance. And the right choice, and it's just a brain twister, the right choice is you take A equals the factor correspond the sigma algebra generated by x goes to mu x v, where v is, say, this group. So you look at the Lever's measure of this v generated by 2 and 3, and the lower unipotent could have taken the upper one as well. Lower unipotent in factor 2 and 3. That's a nice unipotent group, which is the full whole spherical, unstable whole spherical of A0. You look at the Lever's measure. The Lever's measure is some nice measurable map. You look at the sigma algebra it corresponds to. That will be a factor in the sense of measure preserving transformations for the capital A action, and you can look at the conditional entropy. So if you work with this assumption and you obtain the contradiction to this assumption, you actually show invariance under a unipotent subgroup of V. That's kind of a brain twister, and I think I'll stop here. Thank you.
Any questions, comments?